We will continue our discussion of the nearly free electron model by recalling the central equation, which is the equation that connects the coefficients of the plane wave expansion. So those are the basically the Fourier coefficients. And this equation, central equation, tells us that for a fixed k in the first Brillouin zone, the set of k values that we will encounter are c of k minus g and c of k plus g for g negative and positive. So this equation couples those coefficients c of k with c of k minus g1, k minus g2, k plus g1, k plus g2, etc. So we can say this is plus or minus g1, g2, g3, etc., whose wave vectors differ from k by a reciprocal lattice vector g. And these g values are, for example, for one dimension 2n pi over a. So those are multiples of the shortest g value, g1, 2g1, 3g1, etc. So that's what will happen. And for each k value that we will pick in the first Brillouin zone, there are a total of capital N k values that we can pick. And for each of them, we're going to have these g values. And therefore, this is going to give us, for capital N different k values that we will pick, capital N different problems to solve. Now the potential is a periodic potential in the Bloch theorem, and that's sum over GV e to the IGX. And potential energy must be a real function, so the Fourier coefficients must be equal to their minus complex conjugates. And at the same time, because of symmetry in the problem, whether I go in plus g or minus g, the potential profile shouldn't change, so V of g must be equal to V of minus g. Now, if I start with g is equal to 0 here, for the potential, I will have a V0 plus sum over g positive Vg e to the IGX plus e to the minus IGX. Actually, I would have V0 times C of k here. But basically what I'm going to say is I can define the potential with respect to a reference, and I will call this reference V0. So V0 is equal to 0, and I define the potential energy with respect to that, so that this first term will disappear. The second term, sum over g positive Vg e to the IGX plus e to the minus IGX. Normally this would be Vg e to the IGX, V minus g e to the minus IGX, but Vg and V minus g must be equal by symmetry, so there's only one Vg here. And by using Euler's expansion, I can see that the term in parentheses is equal to 2 cosine gx, because I sine gx's cancel. So the potential will be of this form, 2Vg cosine gx sum over g positive, by defining reference potential V0 equal to 0. Now I want to look at this central equation. So the first possible value of k that I will consider is k. So it's lambda k minus e c of k plus sum over gvg c of k minus g. So for the k term, so if k is k, I will have lambda k minus e c of k, and then I will have here for the first g term, I substitute g1, so it's going to be v1 c of k minus g1, so that will be this term here. And then for the opposite parity, so or the opposite sign, if I have v of minus g1, v of minus g1 is equal to v of plus g1, which I call v1, c of k plus g1. So this is going to be the second term here for g1. Now if I use 2g2, so then I will have v of g2, which is v of v2, c of k minus g2, so that will be this term, and c of k plus g2, that will be this term. So this will be an infinite sum that's equal to 0, like this. Now if I consider a possible k value that is outside the Brillouin zone and that is brought back to the Brillouin zone with the reciprocal lattice vector G1. So K minus G1. So that will give me lambda K minus G1 minus E C of K minus G1. So that will be this term here, lambda K minus G1 minus E C of K minus G1. Now I come here for G equals G1, I will have V1 C of K minus G1 minus G1. So this is going to be V of V times V1 times C of K minus G2. So that will be this term. And then for G is equal to minus G1, I will have V minus 1, which is V plus 1. Then I will have C of K plus G1 minus G1, which will K minus G1 plus G1, that will give me V1 C of K. And then for the second term, V2, I will have C of K minus G1, and I'm going to be C of K minus G1 minus 2G1, C of K minus G3, but if it's the opposite sign, then it will be C of K plus G1. So that would be this term, etc. So this continues like this, and for K equals K plus G1, what would happen? Lambda of K plus G1 minus E, C of K plus G1, that is this term here. And then if I substitute K equals K plus G1, for V1 here, V1 C of K plus G1 minus G1 would be giving me V1 C of K, that is this term, etc. So this continues like this. So I can write this for all possible K values, K minus G1, K plus G1, etc. And there are capital N distinct K values in the first Brillouin zone. So that will give me capital N equations. So if I look at the coefficients, C of K minus G2 has a coefficient V1 in the first equation. C of K minus G2 has a coefficient V2 in the second equation. C of K minus G2 has a coefficient V3 in the third equation, etc. And let's look at, for example, C of K coefficients. In the first equation, it is V1. In the second equation, it is lambda K minus E. In the third equation, it is V1 again. So I do this for all coefficients, and I make this table. So if we assume the potential contains only one significant value, that is V1 is equal to V, for the shortest reciprocal lattice vector G, if I go to higher reciprocal lattice vectors, it's going to be the potential decreasing as a function of 1 over G. But that's basically due to the fact that we have the electrostatic potential that decreases as 1 over R. So in the reciprocal space, this will decrease as 1 over the magnitude of G. So we're taking all potentials with higher G values negligible. We're only considering V1. In that case, we will get rid of V2 and V3, and we will substitute for V1. For example, V1 the value V. So for the first equation, we will have V lambda K minus G minus E, V 0, 0, and the other terms will be 0 as well. And then for the second equation, we will have 0, V, lambda K minus E, V, 0, etc. So this is still an infinite set. Now let's consider a K value that is near the zone boundary. So in order to understand what's happening at the Brillouin zone boundary. So we will, in this approximation, assume that only two components are important in the orbital, in the wave functions. And we have K is equal to G over 2, and then K minus G would be equal to minus G over 2, which is minus pi over A. So that is picking a K value near the zone boundary. So to see the effect, we will consider the first free electron energy with no restriction on K values. The energy for the free electron was given by h bar square k square over 2m. Now we're picking k values and k minus g values. So this basically tells us that when you reach a brilliant zone boundary, instead of continuing to the next zone, we can bring the k values outside the brilliant zone with a minus g vector or a plus g vector back to the first brilliant zone. So when we do this, we're basically plotting the rest of the function here outside the brilliant zone, brought back into the first brilliant zone. And when they basically overlap, that means we have already gone through another g over 2 distance in the brilliant zone. That means when these guys overlap, we have reached another brilliant zone. So that's when we start over again, and we have this so-called energy bands. So what we're plotting here is h bar square k square over 2m, or h bar square k minus g square over 2m, or k plus g square over 2m, etc. This is called the reduced zone scheme, that is plotting all the k values, all possible energies in the first brilliant zone by bringing the wave vectors outside the brilliant zone using reciprocal lattice vectors back into the first brilliant zone. And so we can see that here the energy values close to the zone boundary are relatively close, and hence their contributions are comparable. So close to the zone boundary, we can use a two-component approximation for the orbital. We can say the psi is c of k e to the ikx plus c of k minus g e to the ik minus gx. So we're considering the k and k minus g, the traveling waves here, so for different k values. Now the central equation will reduce to a pair of equations. It's going to be lambda k minus e c of k plus v c of k minus g, and lambda of k minus g minus e c of k minus g plus v c of k. So this is basically doing the same exercise for k and k minus g. For k and k minus g, if you look at the first two sets of equations here, by considering v2 equals 0, v3 equals 0, etc., these two equations will give me with the two non-zero coefficients, c of k and c of k minus g, this result. So they have a solution when the determinant of the coefficients is 0, lambda k minus e v lambda k minus g minus e. When this determinant is 0, I can basically see lambda k minus e, lambda k minus g minus e, minus v square must be equal to 0. So if I write this, if I expand it, this will be lambda k minus g, first term, and then I will have e square for minus e, and then the cross terms will be minus lambda k e and plus lambda k minus g minus e, and then minus v square equals to 0. So if I put everything into energy parentheses, e square minus e parentheses lambda k minus g plus lambda k, and then plus lambda k minus g minus v square equals to 0. This is a quadratic equation. I can solve it by using the discriminant. So it's going to be this equation of the form ax squared plus bx plus c is equal to 0. X is equal to minus b plus or minus square root b squared minus 4ac divided by 2a. So you will remember this from basic math courses. So this is what I do here, and I see that there is a positive energy and negative energy, well, E plus and E minus solution. So here minus b is lambda k minus g plus lambda k plus or minus square root b square is lambda k minus g plus lambda k parenthesis square minus 4ac. A is 1 here, so minus 4 lambda k minus g minus v square parentheses divided by 2a. A is 1, so it is 2. So if I expand this, in the parentheses I had lambda k minus g plus lambda k parentheses squared, so it is lambda k minus g squared plus 2 lambda k minus g lambda k plus lambda k squared. And then in the second term, I had minus 4 lambda k minus g plus 4 v squared. So that's what I have here in square root. I can see that minus 4 lambda k minus g lambda k plus 2 lambda k minus g lambda k will give me a minus 2 lambda k minus g lambda k, which will basically correspond to a lambda k minus g minus lambda k parentheses square plus 4v square. And this can be written by taking the 1 over 2 into the square root as 1 over 4. So we get rid of the 4v square 4, we have only v square remaining. So by substituting for lambda h bar square k square over 2m, I have h bar square k minus g square over 2m plus h bar square k square over 2m plus or minus 1 over 2 h bar square k minus g square over 2m minus h bar square k square over 2m. So that's lambda k minus g minus lambda k square. So this is too much here. So this is going to be parentheses square plus v square square root. And then for k prime equals k minus g over 2, that measures how far k is from the zone boundary. We can define this variable. So basically k, we can substitute k prime plus g over 2. When k prime is equal to and g is equal to here 2 pi over a, when g is equal to g, when k is equal to g over 2 corresponds to the brilliant zone boundary, we're going to have this substitution, and this will give us for the energy E plus or minus h bar square over 2m parentheses, we can have 1 over 2 k minus g square plus k square over 2. And then in the second term we have plus or minus 1 over 4 h bar square over 2m square k minus g square minus k square square plus v square square root. So that gives us the second term here. So in the first term we have 1 over 2 k minus g square plus k square. That is 1 over 2 k square minus 2kg plus g square plus k squared. So that it gives us 2k square plus g square minus 2kg. So operating the 1 over 2 here, we obtain k square minus kg plus g squared over 2. And substituting for k prime plus g over 2, I have k prime plus g over 2 square plus g over 2, g squared over 2 minus g k prime plus g over 2. That is, the first one is k prime square plus k prime g plus g square over 4. Then we have g square over 2 minus gk prime minus g square over 2. G square over 2's cancel, gk primes cancel. I obtain k prime square plus g square over 4 for the first term by doing this k prime substitution. For the second term, I have k minus g square minus k square. That is k square plus g square minus 2kg minus k square. K squares cancel. It is g square minus 2g parentheses. For k, I substitute k prime plus g over 2. And that gives me minus 2gk prime minus g squared. G squares cancel and I obtain minus 2k prime g. So the second term becomes here. The second term becomes let's see here 1 over 4 h bar square over 2m square. For the k minus g square minus k square, I substitute minus 2k prime g. So there's the square here, so it's going to be 4k prime square g square plus v square. So that's going to be in a square root. So this is going to be 1 over 4 for h bar square h bar square over 2m. So I have h bar square k prime square over 2m um, plus v square. So there is this, there are two h bar squares here. So it's going to be h bar, if I define lambda to be h bar square g square over 8m, I can see that this is going to be 4 lambda h bar square k prime square over 2m plus v square. So basically, the second term has now become this quantity in square root. So therefore, I have for the energy plus or minus solutions h bar square over 2m, k prime square plus g square over 4 plus or minus v 1 plus 4 lambda h bar square k prime square over 2m v square square root. So I have taken v outside, and I have taken v square outside the parentheses. Now right at the zone boundary, k prime is equal to 0, k is equal to g over 2. So I will have h prime square over 2m, g over 2 square plus or minus v. So that gives me what I called lambda was h bar square over 2m g over 2 squared. That was my lambda. So it is lambda plus v and lambda minus v. So I find that there is a band gap at the boundary, which is 2v. And right at the zone boundary, when k is equal to pi over a or g over 2, k minus g is minus g over 2. The central equations give me, if I go back to the central equations, they give me lambda k minus e times lambda minus e times c of g over 2 plus v of c minus g over 2 here. When I substitute k is equal to, this is k is equal to g over 2. And for the k minus g equation, I substitute k is equal to minus g over 2. So these two equations give me the following result. Lambda minus e over v is equal to minus c of minus g over 2 divided by c of g over 2. And lambda minus e over v from the second equation becomes c minus c of g over 2 over c of minus g over 2, which tells me c of minus g over 2 is plus or minus c of g over 2. So that gives me the coefficients, the relationship between the coefficients. So in summary, we have found that the central equation gives us two solutions for the energy of a particle with a wave vector at the zone boundary, lambda plus v and lambda minus v, where lambda is h bar square k square over 2m when k is equal to plus or minus g over 2. And v, what is v? It's the first Fourier coefficient of the potential. So the band gap in the first Brillouin zone boundary is twice the first Fourier coefficient of the potential. So let's summarize what we did here. We looked at the central equation, and we have written the central equation as infinite, by considering the infinite sum, but we have capital N equations for all possible k values in the first Brillouin zone, and k vectors that we consider are of the form k minus g1, k plus g1, k minus g2, k plus g2, etc., where g1, g2, etc. are multiples of the shortest reciprocal lattice vector. For example, for 1D it is 2n pi over a. And so by considering the one-dimensional case here, we're basically considering the one-dimensional case. We can write the potential as 2vg cosine gx sum over g positive by defining v0 to be 0. And then the second simplification we did was we don't consider the potential second Fourier or third Fourier coefficients, because vg values will decrease as 1 over g, because the potential energy decreases as 1 over r. For electrostatic potential. The same thing applies to the reciprocal lattice here. So by considering this, we have written the determinant of the coefficients for the case we have only non-zero potential values in the first Fourier coefficient, and by considering k minus g, and k plus g, we have written this explicitly. And now we have introduced the concept of reduced zone scheme. So anything outside the first Brillouin zone, we can bring back to the first Brillouin zone by using an appropriate reciprocal lattice vector, minus g or plus g. And you can see that when what we have brought back overlaps, we basically have reached another zone boundary. So this would be k is equal to pi over a. This would be k is equal to 2 pi over a, and then we would have k is equal to 3 pi over a, etc. here. So this would continue like this. And near the zone boundary, we can assume that we have a two-component solution. Basically, that is motivated by the fact that if you look at the energy values near the zone boundary for k vector and k minus g vector, these two are almost giving the same energy value here. So those two solutions should be considered, k and k minus g at the zone boundary. And if we look at this case for the central equation, that gives us for the Fourier coefficients this equation, which has a solution when the determinant of the coefficients is 0. And by solving this determinant, we have found that the energy has two possible solutions, lambda plus v or lambda minus v, where lambda is h bar square k square over 2m, and k is plus or minus g over 2 at the zone boundary. So we find that if we plot energy versus k, the free electron solution for k is equal to g over 2, which is pi over a, was like this. But for the nearly free electron model, we have a first band and a second band forming, and there is a band gap here, which is how much? So this band gap is equal to 2v, that is or equal to 2v1, the first Fourier coefficient. So that's at the first Brillouin zone boundary. And furthermore, we looked at the coefficients c of g2 and c of minus g2, and we found a relationship with these coefficients as well. So basically this gives us explicitly the result that we should expect a band gap at the Brillouin zone boundaries. And so we have this formation of energy bands here in the free electron model. So this picture should be modified by considering the fact that we should have band gaps at the zone boundaries. So we should replot this picture by using the band gaps instead of having no gaps at the zone boundaries. So we will continue this discussion by considering the one-dimensional case explicitly again, and we will see that this zone boundary really stems from the fact that we have standing wave solutions at the zone boundary, and we have the Bragg reflection condition satisfied, or von Laue condition satisfied, and these traveling waves that are traveling to the right of the zone boundary and to the left of the zone boundary will interfere to give us this these two solutions with two different energies.